This topic is very interesting not only to the students of chemistry, but also to the students of physics, metallurgy, chemical engineering, material science and geology. By the end of this series of lectures, you will be able to find out answers to the questions like why pure substances have sharp melting and boiling points, why certain substances sublime, how distillation can be carried out effectively, how alloys are formed, why there are large deposits of crystals of rhombic sulfur. The crystals are very large in the nature, as well as to the questions like the ones that you come across in your daily life. How food gets cooked faster in a pressure cooker? Is the title of the film "Diamonds Are Forever" correct? Such and other things you will be appreciate after going through the entire lecture series on phase equilibrium. I'll start my lecture by giving definitions and explanations of some of the terms which you may know, you may have come across, but you may have to attach newer meanings to these terms. The terms are system, homogeneous system, heterogeneous system, equilibrium, metastable equilibrium, processes involving heterogeneous equilibria. And I'll conclude the lecture by introducing you to the very important rule in phase equilibria called the phase rule. Let me start by introducing you to the definition of the term system. Thermodynamics defines system as that part of the universe which is under consideration. That means we are dividing the universe into two. One part is the system, remaining part of the universe is called the surroundings. The system and the surroundings are separated by a well-defined boundary. The boundary may be observable or may be imaginary, and this is drawn by us for our convenience. We can define the systems and classify them. Take this example of a glass containing water. Water may be hot, may be cold, but if you leave it on the table in the lab, the water ultimately attains the temperature of the room, which means the system water is able to exchange heat across the boundary. Across the boundary means between the system and the surroundings. Now, some of the molecules of water may gain energy and escape to the surroundings, and at the same time some of the molecules may return to the water. Therefore, matter is also exchanged between the system and the surroundings. Such systems are called open systems. Now, we have water or a solution in a bottle that is stoppered. That means we are preventing the vapors or the molecules to escape or return to the system. But the heat can still be exchanged between the system and the surroundings. Such systems are said to be closed systems. In this, we have taken, say, water in a thermoflask, an insulated flask. In this case, neither heat nor matter can be exchanged between the system and the surroundings. The system is said to be an isolated system. Suppose we want to study the system water. How do we study it? we want to study the effect of temperature and pressure on water. In such a case, we'll take water in a container that is fitted with a piston so that pressure can be applied, and also we make provision for heating or cooling. Such a device is fitted so that we can study the effect of temperature on such a system. There is another way of classifying systems, and one type is a homogeneous system. We describe a homogeneous system as the one in which the properties of the system are uniform throughout. It has the same composition. Like a solution of alcohol in water, the beaker that is shown may contain pure water, maybe pure alcohol, maybe a mixture of the two. But any sample taken from the beaker will have the same composition. We can elaborate and find out more examples of it. If you take a gas or a mixture of any number of gases, it will still be a homogeneous system because we know that gases are miscible in all proportions. And the best example that we have is air that we breathe. When we breathe air, all the gases that are present, nitrogen, oxygen, and those gases which are present in smaller quantities all get into our lungs. It is not possible for us to breathe only oxygen. Take a mixture of miscible liquids, the one that we just stated, alcohol and water, which are completely miscible. You can also take acetone and alcohol or mix all the three. The system still will be homogeneous system because all the three are miscible liquids. But if you take solids, we don't know. We'll defer the answer to a later stage. The other type is the heterogeneous system. It describes a state of matter in which the properties are not uniform throughout. Like a saturated solution of salt in water, you can see the supernatant liquid, which is the solution, and the solid, which is settled at the bottom. We can try to elaborate with more examples. A mixture of immiscible liquids like chloroform and water, where the denser liquid settles at the bottom, the lighter liquid floats on it, and we can see a clear boundary that separates the two. An interface is formed between the two liquids. If there is one boundary, there are two liquid layers. If there are two boundaries, there will be three liquid layers. In the case of partially miscible liquids, the resulting mixture may be homogeneous or may be heterogeneous. If the solubility limit is not exceeded, the resulting mixture will be homogeneous, like phenol and water. You take phenol and add water dropwise, phenol can dissolve sufficient amount of water in it, and vice versa. But in either case, if you add excess of one into the other, the resulting system becomes milky. That means it becomes heterogeneous system. In the case of solids, it is generally said that each solid constitutes a separate phase, and hence the solids will form heterogeneous systems always. You take, for example, a mixture of sodium chloride and potassium chloride. Both are white solids, glucose and fructose. Even the allotropic mixtures like rhombic sulfur and monoclinic sulfur form separate phases, and therefore they are said to be heterogeneous mixtures. There is exception to it. When two solids can form what is known as a solid solution, probably you are coming across this term for the first time, the system is a homogeneous system. Like sodium chloride can dissolve in water to form a clear solution, alcohol can dissolve in water to form a clear solution. one solid can dissolve in another solid to form what is known as a solid solution. An example of this is a solid solution formed between gold and silver. We will discuss more about it when we come to the systems involving solid solutions. Now, another interesting term which you think you know is equilibrium. Physical equilibrium, in which there is only change in the state of matter, like water liquid in equilibrium with water vapor, it is water on either side, H2O. Similarly, we can have ice in equilibrium with liquid water. We can also have chemical equilibrium, like the decomposition. In this case, calcium carbonate decomposes to give calcium oxide and carbon dioxide. In some cases, it can be a mixed equilibrium in which both physical and chemical equilibria may be simultaneously present. I will show an example here. Ice water equilibrium at 0 degree centigrade. Ice melts, and at this junction heat enters and tries to melt ice, and water may get cooled in the vicinity of ice and get frozen. So, there is an equilibrium established at the junction. We can define equilibrium thus: equilibrium exists in any system under a fixed set of conditions when the part of the system do not undergo any change of properties with the passage of time, provided that the parts of the system have these same properties when the same conditions are again arrived at by different procedures. The definition looks longer and slightly different from what you have come across. Thermodynamics defines equilibrium thus: a true equilibrium is attained when free energy of the system is at a minimum value for the given value of variables operating on the system. Let us elaborate this by taking an example. All of us know that pure water has a freezing point of 0 degree centigrade, and therefore, we expect water to be a solid, that is ice, at -5 degree centigrade. But if we take a sample of water, clean water free of dust, and cool it slowly, steadily, without giving any vibration, the temperature decreases lower and lower, and as we approach 0 degree centigrade, we expect it to freeze, but then the temperature goes below 0 and it can reach up to -5 degree centigrade and water still be in the liquid state. Unbelievable, isn't it? Then we can keep this sample of water as long as we want without disturbing. Therefore, the fact of mere remaining in a state unchanged with time is not enough to define equilibrium. In this case, we know that the water at -5 degree centigrade is not in equilibrium. This is not the thermodynamic equilibrium state. If we disturb it by seeding it or by stirring or shaking, it suddenly changes to ice, it freezes. The temperature rises to 0 degree centigrade. We can also try an experiment starting with a piece of ice at -15 degree centigrade and slowly warm it up to -5 degree centigrade, as shown in this figure. We expect, as in the earlier case, ice to melt at -5, but nothing happens. Ice melts only when we attain the temperature of 0 degree centigrade, which means that liquid water at -5 degree centigrade can be obtained only by cooling water and not by heating ice from lower temperatures. So, we can redefine equilibrium a state of true equilibrium is said to exist in a system when the same state can be attained by approach from either direction. Then what about the liquid water at minus 5 degrees centigrade? It is said to be in a state of metastable equilibrium. It is called supercooled water. Such a state can be realized only by careful approach from only one direction. A state of unstable equilibrium is said to exist when the approach to equilibrium in a system is so slow that the system appears to undergo no change with time. There can be a resistance somewhere in the system forming the reason. Take the example of a saturated solution of salt in water. It is a nearly saturated solution and you try to add more salt to it and you find that some salt has settled at the bottom, and if you watch it next day, you may be wondering what has happened to the salt. Whatever little salt that was there at the bottom may have dissolved. That means in this case it was not the equilibrium state that you saw yesterday between solid and the liquid. It is the insufficient time of observation. If you had left sufficient time to pass by, the salt would have dissolved. It is a case of non-equilibrium. Therefore, it must be realized that metastable equilibrium at least represents a state of partial stability, whereas unstable equilibrium is a misnomer. It does not involve any equilibrium at all, but only a process of very slow change. Let us describe some of the systems in which you come across heterogeneous equilibrium: vaporization, sublimation, fusion, transition of one solid phase to another, distribution of solutes between phases. And each type of heterogeneous equilibrium we have tried to use different methods to treat them, and some of them are Clapeyron equation, Clausius-Clapeyron equation, Raoult's law, Henry's law, law of mass action, Nernst distribution law, etc. So, if you have a case of two immiscible liquids in equilibrium and if you add a solute into it, the solute distributes, and we know that we have to use Nernst distribution law. If we have to find out solubility of a gas in a liquid, we then apply Henry's law. So, that way we know for each type of heterogeneous equilibria which equation has to be used. It depends fully on the information that we want and the type of system that we are going to study. But the scope of heterogeneous equilibria is so wide and their types so diverse that the above laws cannot cope up with the diversity of the problems arising in these cases. But we also would like to have one law or equation that is applicable to all types of heterogeneous equilibria, and this is possible by means of a principle called the phase rule. That is, phase rule can be applied successfully to all types of heterogeneous equilibria. With this principle, the number of variables to which each and every type of phase equilibrium subject to may be defined under various experimental conditions. By this definition, the phase rule does not invalidate or supersede some of the methods that we have seen earlier, like Clausius equation, Clausius-Clapeyron equation, and Nernst distribution law, etc. There is one advantage of phase rule. It is that it is independent of any assumption based upon any theory, such as the molecular theory, theories of constitution of matter, or theories of chemical reactions, etc. Because of the changes in understanding of such theory, we had to modify or discard many of the laws that we evolved over the years. But in this particular case, phase rule is not subject to revision or rejection, as our views on these matters may change. This is because it has withstood the test of time. It is not subject to revision or rejection. But there is one disadvantage which the phase rule suffers from, that is, it cannot always yield quantitative information regarding the equilibrium when it is applied. The phase rule is merely able to fix the number of variables involved, but the quantitative relations among the variables must be established through supplementary expressions such as some of those we saw above, like Clapeyron equation, Clausius equation, etc. In other words, all information which we can know from phase rule is qualitative in nature, but the extensive fields where the rule finds successful application and the reliance which we can place upon it far outweigh the importance of the limited quantitative information available by the help of other laws and equations. This law was enunciated by Josiah Willard Gibbs in two parts in 1876 and 1878, but the contemporary scientists did not accept it, did not welcome it. One of the reasons could be that it involved lot of abstract mathematics, but subsequent development of the subject is due to the work of Roosboom, who extensively studied Gibbs' work at the advice of van der Waals and came to the conclusion that phase rule is a principle of widest applicability, of highest value in the classification of heterogeneous equilibria, and of greatest reliability in settling disputed points. All superlatives used. Roosboom wrote a book which made the treatment easy and indicated the importance of the rule in different subjects. The works of Ostwald and Van 't Hoff further added to the importance of the rule, and today phase rule is recognized as one of the foundation stones of physical chemistry and chemical thermodynamics. Let me summarize what we studied today. We started with definition of the terms like system, homogeneous system, heterogeneous system, equilibrium, metastable equilibrium, and some of the processes involving heterogeneous equilibria. And finally, we discussed about phase rule, one equation that can be used to deal with all types of heterogeneous equilibria. In my next lecture, I will elaborate on phase rule and the terms that are involved in it.